Not that complicated. With Ava and Jacob.
Welcome back to another video with Jacob, and today we'll be taking up 2D equilibrium. Below we have a simple example, and while I read the question, I like to physically draw out the dimensions so I get a better idea in my head. The question states, a hanging monkey is holding two ropes that are attached to trees separated by 9 meters, as shown in the diagram. The ropes are 5 meters and 7 meters long. If the mass of the monkey is 35 kilograms, determine the tension in the 5-meter long rope. Since we're dealing with forces, I always like to visualize all the forces that are going on in the system using a free body diagram. It's important that you label the free body diagram because you'll use those labels throughout your calculations, and it's better to stay organized. The question requires of us to find the force of tension in the 5-meter rope, which I labeled FT1. The most important concept is that the monkey is not moving. In physics, if something is stationary, all the forces pushing and pulling on it must cancel each other out perfectly. We call this static equilibrium. In the real world, we don't always know the angles, but we do know the side lengths. Since the ropes and the gap between the trees form a triangle, we can use the law of cosines to find the angles. Since we have the length of all three sides, we can use the law of cosines formula right below. The side length C in this case is 7 meters. We are going to decide that this length is 7 meters. And in the cosine law formula, the angle is always the angle opposite to that side. Instead of keeping this angle called C, we're actually going to make it called theta. Now we plug in our values where C is 7 meters, A is 5 meters, B is 9 meters, and we continue the formula. Now we can rearrange this formula so that we get a value equals cosine theta. Once we have this, we can do the inverse of cosine of the value on the other side of the equation equals theta. So in this case, when we plug in the cos inverse of 19 over 30 in our calculators, we get a result of 50.7 degrees for theta. Now let's work on the other angle across that the 7-meter rope is experiencing. We'll name this angle theta 2. The process is identical to when we found the angle for theta 1. Instead, in this case, the side length across from theta 2 is 5. So now we just plug in our numbers, we isolate and rearrange for cos theta 2. We then get 5 over 6 equals cos theta 2. We rearrange, and the inverse of cos, 5 over 6, is 33.6 degrees, and that's our value for theta 2. Now we can set up our equilibrium equations. We're first going to start off with the weight of the monkey. The weight of the monkey is just its mass times the acceleration of gravity, and that gives us 343 newtons. Okay, I'm going to quickly redraw our free body diagram so it's more clear. I'm also going to put our corresponding angles on the free body diagram so that we can calculate the angles and the forces in the y and the x a little bit easier. So since we know that our system is in equilibrium, we know that the sum of forces in the x direction need to be equal to 0, and the sum of the forces in the y direction have to be equal to 0. And it's also important to set the direction. Here I am choosing to the right as positive x and up to the positive y. So here I am doing the forces in the x direction, and I'm doing negative ft1 because it's going against the direction of the motion I set as positive x. So therefore it's negative ft1 cos theta plus ft2 because it's going in the positive x direction, cos theta 2. Now we can isolate for ft1 so that when we sum the forces in the y direction, we can just plug in that value and get that equation in terms of one variable. So then again, for y direction, we're setting upwards as positive. I'm just going to copy our free body diagram and repaste it where we're working so that it's a little easier to understand where and how I'm calculating the forces in the y direction. So ft1 sine theta, it's positive because it's going upwards, and it's sine theta because the y component is opposite to the angle. And same thing goes with ft2, and for the weight, it's going in the downwards direction, which is negative. That's why it's negative w, which is its weight. Now, rethinking about what the question is asking to find ft1, it's better if we isolate for ft2. Therefore, we can plug in ft2 in terms of ft1 into our equation and get the entire final equation in terms of ft1, so that we don't have to do even further calculations and deal with more equations after that. So now when we see ft2, we plug in our equation so that we can get them in terms of ft1. Now that we finally have it in terms of ft1, we can now plug in our numbers and work this out numerically. We get ft1 sine 50.7, and now I'm multiplying and dividing all of these small cosines and sines so that we can get it in terms of an actual number. Now, this number is going to be very small, and it's important to keep all the decimals because they're important to keeping the final answer accurate. Now, ft1 and ft1 are both the same variables, so now we can add just like we would if ft1 was x. Now we can isolate for ft1, and finally we get that the force of tension in the 5-meter rope is 287.1 newtons.
Thank you for watching Not That Complicated. Don't forget to like and subscribe.